Fill a tank with petrol and burn it in a modern car engine, and even when that engine is operating at its absolute best, less than half of the fuel's chemical energy will ever reach the crankshaft as useful work. Engineers account for this using brake thermal efficiency. It is the precise fraction of the fuel's energy, measured by its lower heating value, that successfully delivers physical rotation to the output shaft. For the most highly optimized production gasoline engines on the road today, that peak efficiency sits in the low 40s. The remaining 60% of the energy is immediately shed as heat. This 60% loss is the baseline for a modern gasoline engine, representing the current boundaries set by thermodynamics and material science. That missing 60% of energy leaves the system through a few well-defined, measurable paths. The first and largest leak is the hot exhaust gas leaving the cylinders. Roughly a third of the fuel's total chemical energy is blown straight out the tailpipe. The cooling system acts as the second major leak. To keep the engine block from failing under extreme temperatures, the liquid coolant absorbs nearly another third of the energy directly from the cylinder walls and head. While these exact proportions shift depending on load and speed, the overarching structure holds consistent. Exhaust heat and coolant heat are the two most massive, unavoidable drains on the system. To see why we cannot simply capture that wasted heat, we have to look closely at the physical work the engine actually manages to extract. An internal combustion engine generates work by taking heat in and rejecting the rest. Thermodynamics caps this work at the Carnot limit. Real-world gasoline engines use the Otto cycle, contending with finite combustion and hot exhaust, which pulls the practical efficiency ceiling even lower. The vast majority of the heat dumped into the exhaust and coolant is energy the laws of physics never allowed the engine to use in the first place. To squeeze more work out of the heat they are allowed to use, engineers rely heavily on the compression ratio. By compressing the air and fuel mixture more tightly before igniting it, the cycle extracts a higher percentage of useful work from the exact same amount of thermal energy. But gasoline limits this lever. If engineers push the compression ratio too high, the chemical mixture spontaneously auto-ignites. This creates engine knock, a violent pressure spike that shatters components. Diesel engines bypass this by compressing air alone and injecting the fuel later. Free from gasoline's specific volatility, they can safely run much higher compression ratios and achieve higher thermal efficiencies. The chemical volatility of gasoline sets a specific, hard limit on how much efficiency can be extracted through compression alone. Even after thermodynamics and chemistry take their cut, the engine must pay a mechanical tax inside the block before any rotation reaches the transmission. The first is friction loss. Sliding metal surfaces, like piston rings dragging against cylinder walls, along with driving accessories like oil pumps, consume a measurable slice of the generated work. Then there is pumping loss. The engine acts as a massive air pump, expending valuable energy simply drawing fresh air past a partly closed throttle and forcing the spent exhaust gas out. These breathing restrictions are especially severe at part-load operation, which happens to be exactly where passenger cars spend the vast majority of their time. This part-load penalty is the reason engineers use downsizing and turbocharging. Forcing a smaller engine to work harder at a higher load keeps the throttle open wider, shrinking those pumping losses. Consistently hitting 40 or 41% efficiency in a mass production engine family, like Toyota's Dynamic Force, requires optimizing every individual system to its absolute limit. In specialized motorsport environments, hybrid engines have pushed past the 50% barrier, utilizing incredibly expensive setups that do not translate to road cars. To chase that 50% mark for everyday drivers, researchers are deploying complex combinations of dilute combustion and advanced waste heat recovery systems. The straightforward efficiency gains were captured decades ago. Today, every new fractional percentage point requires an immense increase in mechanical complexity and development cost. Moving the needle further demands a clear-eyed look at the data, separating the strict thermodynamic walls we cannot break from the mechanical taxes we can slowly chip away. You can explore the exact mathematical boundaries, thermodynamic breakdowns, and professional engineering resources that map out these physical limits online. Understanding exactly where the physics stops us is the only way to build real-world machines that push right up to the edge.